Welcome to Introduction to Quantum Field Theory, Lecture 14. In this lecture, I will set up the concept of Feynman diagrams. To get started, recall that in Lecture 12, we set up a perturbative expansion for the pressure, such that the pressure in interacting quantum field theory is given as the free pressure plus a correction that involves the first order of the coupling constant, a second order term, and so on and so forth. The first order perturbative correction was given as an expectation value of the interacting action. To second order, we had an expression that involved the expectation value of the square of the action minus the expectation value of the action squared. In the last lecture, we discussed a theorem, namely Wick's theorem, that let us recast this first order perturbative correction as an integral that involves the expectation value of only 2-point functions. We will call this object that appears in these 2-point functions or in these integrals that involves two insertions of the field phi, the free propagator or free 2-point function. This object represents how information gets passed from one point x to another point y through the quantum field theory. Since it basically represents how information gets passed from x to y, we can represent it pictorially as a line from x to y. If we wanted to calculate the first order correction to the pressure, we need to calculate the propagator where the position x and y are the same. So basically we have phi of x, phi of x. This means that the arguments of phi are the same, so the line starts at the same point as it ends, and therefore it can be represented as a loop. In the case of the first order pressure, we have two of those propagators that close onto themselves. So we have two loops to consider. There's a coupling, lambda, that is just a consequence of the first order perturbation theory, and we'll denote that coupling as a dot in the pictorial expansion. So we get that the first order pressure, P1, is just given as the two loops for the two propagators and the dot for the coupling. This pictorial representation of the two loops and the dot is called a Feynman diagram. This Feynman diagram contains all the relevant information that we would otherwise have encoded through the integral. We already know what the line means, namely it's just the 2-point function phi of x, phi of y. Now let's just add a rule that whenever we see a dot, that means a vertex, meaning that we have 4 legs connected to this coupling constant of lambda, and we decode this symbol to mean minus lambda, where the minus is just a convention. When we do that, we have to keep track that there have to be certain factors that tell us how many ways there are to connect the different legs in the diagram. This is the combinatorial factor. To demystify those rules, let's just do an example. Let's start with a single vertex that we said was just denoting minus lambda, the coupling constant. Now let's pick one of the legs and connect it with another leg. Maybe we pick this leg here and we connect it with one of the other legs. So maybe this one over there. If we do that, we get one loop. And since we could have picked all of the other legs as well, there are 3 possibilities to do this. So we get an overall factor of 3. Also, because we've closed the loop, we now have a line, and the line corresponds to a propagator that closes onto itself. So we have phi of x that represents this loop here. Once we are at this stage, we pick another leg, let's say this one, and we connect it with another leg in the diagram. There's only one left. If we do that, we get a second loop. And since there was only one other leg that we could connect the leg that we picked, there's just a combinatorial factor of 1. So we just get another propagator. So then this diagram here represents -3 lambda times propagator and another propagator. Returning to our setup of Feynman diagrams, we find that the first order diagram that is generated by this vertex here corresponds to this loop here, which is nothing else but our first order perturbative contribution to the pressure. If we reinstate that there has to be another rule that includes that we have to integrate over the propagator here, then we find that the first order pressure, or this diagram here, is just given by this expression -3 lambda times 1 over beta v times the integral of the two propagators. Basically, Feynman diagrams are nothing else but a shorthand notation for integrals that occur in perturbation theory. You don't have to use them. They basically sort of represent exactly the same amount of information. If you want to use them, basically you have to start by figuring out what the so-called Feynman rules are, what different elements of a diagram correspond to in usual integral notation. The Feynman rules can be formulated either in coordinate space or just x space, or they can be formulated in momentum space. It is possible to express perturbation theory in terms of Feynman diagrams. And if we do so, there are some elements that actually are simpler if we think of perturbation theory in the Feynman diagram sense. Most of the simplifications occur at higher order in perturbation theory. So if we limit ourselves to low order perturbative results, there's essentially no direct gain by using Feynman diagrams. So we can as well use the integrals. And that is essentially one of the reasons that I haven't really spelled out the Feynman rules for this interacting quantum field theory in great detail. Most of the time, it would be perfectly fine for us to work out the integrals directly without having to recurse to Feynman integrals, Feynman diagrams. It is hard, but not impossible, to express full, meaning non-perturbative results of the quantum field theory using Feynman diagrams. Because typically what it means is that you have to think of an infinite number of Feynman diagrams. Because of that, Feynman diagrams are most useful in perturbation theory, meaning that their use is mostly limited to regimes where the coupling lambda is very, very small. However, let us just point out the power of Feynman diagrams in a simple example. To this end, let us consider the second order perturbative result for the pressure, P2, that in terms of the formulation in perturbation theory was given as this expression: the expectation value of the action squared minus the expectation value of the action squared. If we expand the expectation value of the action squared in terms of Feynman diagrams, we have to remember that second order perturbation theory means two vertices. So we have two dots, and we draw all the diagrams that are possible with two dots. So if you have two dots, there will be a diagram that has these three loops. There will be a diagram where we connect the two vertices such that they close onto themselves, and I represent this by a cross in the middle. And there will be a diagram where the two vertices are fully connected so that all the legs basically run between the two vertices. The diagram where there is no direct connection between the vertices is called a disconnected diagram. Basically, that is just an obvious nomenclature. That a disconnected diagram is just a diagram where there is at least one vertex that's not connected to the rest. So in this case, clearly there is no connection between these two vertices. So basically these two contributions factorize. This generalizes in a straightforward fashion to higher orders in perturbation theory, and we just refer to diagrams where one vertex is not connected to the rest of the diagram as a disconnected diagram. So let us recall that we have the expectation value of the action squared be represented in Feynman diagrams as the upper line. And from perturbation theory, we found that the first order expression for the expectation value Si was just this double loop here. So if you then take the square of the double loop, you basically have the product of these two diagrams, and that is just our disconnected diagram from before. Now, if we sort of put these two together, remember that there is a minus between these two terms. So that means that this disconnected diagram that is present in the expectation value of Si squared exactly cancels against the expectation value of Si squared. And we only have connected diagrams left. So these are these three loop and something that is sometimes called a basketball graph. It turns out that this cancellation of disconnected diagrams in the pressure to second order is not a coincidence. We can actually show that this happens generically for all physical observables, and the pressure is a physical observable, to all orders in perturbation theory. So you never have to deal with disconnected diagrams in these observables so that the corresponding calculation gets considerably simpler. Essentially, the simplification comes from the fact that we have this logarithm in play, and that sort of leads to the fact that the physical observables can be expressed as just an expansion of connected diagrams when we calculate in perturbation theory. Clearly, while at second order in perturbation theory, it's not that much of a sort of simplification, you can maybe sort of appreciate that as one goes to higher and higher order in perturbation theory, being able to have a simplification rule such that we only have to deal with connected diagrams leads to major simplifications of the setup of the calculation. And this concludes the present lecture.